cloud, and we are recording then. So we are recording, and two of us are participating. Krista and I, and Kevin's in the room, and so much for here we are all for the class. Most of the other people maybe watching the primaries. Kind of a busy week since we were here last. State of the Union address, impeachment vote, and we'll get the New Hampshire primary today. See how that all plays. Let's from the beginning. Okay, what do we have? We have, let me see if I can get a pointer here. It's February 11th. There's a few little R things, but not too much. I didn't actually get through putting all the slides together for this chapter 5 second edition. It's a little longer than some of the other chapters, but I do have, I think, over 70 actual slides. Some I have in that list. If you happen to download the slides, you get you'll see some blank ones there. I'll fill those out probably for reference and go over some of those topics further on. What we'll do is start chapter 2 of FPP, and I think I have a couple of pictures from the first edition. They chose to do the topics in a very different order in this chapter in the second edition. Usually you don't see that much change in textbook from edition to edition. Rarely do you get a change in order of topics. I mean, they'll put a few things in and take a few things out, but you just don't usually see this chapter's rewritten in a whole different order. When you're an instructor, who has to do a lot of slides, you sometimes wonder how much you can get out of the old edition slides. That means carefully comparing the books and making sure you didn't lose anything. So, especially when you build them yourself. And that's the old graphic. There's some newer ones out. Maybe we'll update this. And same contact information. Yeah, I do have my phone charging. So the live login is still working. I do have one. And there are a bunch of ways to get to that streaming video now. The 4 I put up in previous years, and then the connection through the main Zoom and D2L. It's like, and then the email links, I guess. So what, 8 different sort of pathways to start to get to the video. But there really are just 2 forms of it. I didn't get this up till Thursday last week. Wednesday was a little busier than I thought. Yeah, I haven't got assignments together yet. But this is the big news item, exam 1. The study guide's been out. I think that got out last week. Maybe it was the week before. Yeah, okay. And the study guide's kind of detailed. I think that ends up being, well, making the course maybe a bit too easy in some people's minds, but I haven't had many direct complaints about that. Yeah. In fact, I've had a few people say they truly appreciate just giving this long study exercise and then having it be worthwhile. I mean, that just seems like sense, right? Here, I pile a lot of work on you, you get a good grade. Leave out the worry. Kevin seems to think that's generous. You're not going to complain, huh? At least not to my face. No. 2 exams and assignment equally weighted. There may be suggested problems with my solutions. Yeah, I haven't got much into that. Oh, who's here? Who's here? Oh, I guess we can see. Ace. So I have somebody with that last name in all my 3 classes at 2 different schools. Wow. Didn't realize it was all that common a last name. I had one class with 3 people named White in it one time. So I could even joke about that with folks. Oh, someone else. Brian Clapham. Okay. Welcome to Brian. All the stuff on our 3 weeks ago we did do the install in R. Demoed it live. It's brave, I think. I don't know. It's like I try to show how to use the computer. I mean, yeah, if it's an Excel function you click on, that isn't so bad. But try to run and install. I don't know. Okay, here we are in the list of things. We talked about time series graphics, tool, forecaster's toolbox, the judgmental side of things, and now finally, actually some real stuff. Next week, time series decomposition is actually probably the most classic approach to time series, and then we start stepping away from the more classic ideas. Then dynamic regression models, advanced some things about R. We'll see what we get to. Have some fun with things. And wow, a lot of topics here. And I kind of got to about here in making up slides. So that's about all I have for today. So what do we have? We have some terms. We call y a basic concept is we have y with other time series of x's in time series regression. So we have a number of time series, and some of these things, kind of things economists might want to play with. Got a bunch of variables running around and from governments, and we want to try to predict an interest rate or a stock price or something like that. Uh, Nothing so miraculous. Where some of the other forecasting is sales forecasting. However, and then predictor variables are sometimes called the regressors or independent or explanatory variables. So different books. Okay, so regressant, dependent, or explain. There are so many books that just try to beat people with the difference between dependent, independent. This forecast and predictor is so much clearer and almost I almost explain the other terms with predict response. Uh, Forecast has a time inference, but it's still there. Okay, so x and y and x, and simple linear regression has a few terms. This is an intercept. This is a slope. This is the variable at the time, and this is an error term. So we start modeling it this way, and we assume the world works this way. There is some parameter beta naught, which is here, the intercept, and a slope, and we can draw a line in x, and then we can also draw our model line, and every time we get a little playful little error, it generates us a point off our line at a particular x. And we can get sample data and play games fitting it, assuming this is reality. And this is simple linear regression, and I don't know what you probably saw this a long time ago. High school junior year for me. Oh yeah, it was a special class, and teacher gave me a book that she normally wouldn't have given folks. But it was called Futuristics. It had this stuff in it. Maybe she knew something. Okay. So we have this consumption data and consumption income for this US change variable in our stuff, and we can get this plot of consumption versus income. And well, those look like they might make an interesting plot. So percentage changes in personal consumption expenditure and personal income um, uh, for the United States. So economic kind of stuff. Um, uh, Two lines overlap, and second edition type graphic. Not different this time. we have a new function, TSLM, and it works kind of like LM. Uh, now, for those of you who've taken 382 with math department, you will immediately say, "Oh yes, I beat that up for for about 10 weeks," and there it gives some results. And if we run it for this consumption versus income with the data US change, we get the slope and intercept of these values. And with a few other commands, which are given in the online book, so much advantage to have an electronic book, especially if you cut and paste those things. Yeah, you can get it in paper, but that's a little harder to get the command in. Suppose you could have a camera and some software, but that's a lot of trouble. But yeah, there's the scatter diagram from the data, and then that's that fit line. And those are quarterly changes of consumption versus personal income. So people spend more when they make more, generally. Multiple linear regression. Now, that was a simple linear regression, one variable. Multiple means we have multiple variables, more x's, and there are k predictor variables. So we go from 1 through k in this book for subscripts. And we have betas. So the predictor variables, when we call it multiple linear regression, must be numerical, and the beta measures affect each predictor after taking the accounts of all other predictors in the model. So yeah, so it's a coefficient, but coefficients actually end up changing a bit if you change the sets of predictors. Oh, somebody's here. Let's see who we have. Kevin Thompson. Kevin Thompson. Okay. See Kevin. I
Hey, how's
don't
it
know.
going?
Okay. Okay. Uh, I was just trying to think. Had you in so many classes. I, I don't know. Must be like 6 or something. I don't know.
Yeah. Yeah, well, this is my last one with you, so
Last one. Okay. I know we can find a different way to have another class with Kevin Thompson. All right. Let's see, can I find another way to have enough? Maybe I'll have to start giving workshops and inviting Kevin to attend. Here, Kevin, another workshop just for you. Okay. Uh, taking into account the effects of all other predictors in the model. Okay. Um, all right. The coefficients measure then these marginal effects of the predictor variables. So if I throw in a little more of x1, get it, the thing will change in proportion to beta 1. Um, so nice kind of function there. And we had income that would help us predict consumption, but what about production? What about savings? What about unemployment? Oh, yuck, the percent change in unemployment. Uh, yeah, there are some times, huh? Right? Yeah, that's when I was happy to get a state government job. Yeah, with that spike. And so The figure 5.5 shows a scatter matrix of the related predictors. I didn't, the scatter matrices get, these look pretty detailed, these graphs, but those scatter matrices, they're pretty detailed with 5 um, uh, on a screen here, at least for me to see. uh, so gives you some thoughts of what we can look into. Um, so in a linear regression model, we're making some assumptions, more so than you might think. Uh, I, I guess first of all, when we try a model and this happens with everything, we just assume it's a reasonable approximation to reality. The things step up in proportion, at least over the ranges we're playing with. Uh, Sometimes over a short range, a linear approximation works. I um, when we interpret do interpolation of tables, we make that assumption in a short range linear works. I don't know how much that's taught these days. Uh, no, I really. Uh, Second, about the errors, we assume they have mean zero. Um, Else, their forecast. If you don't have a mean zero in your errors, um, the forecasts are systemically biased. So you would really just want to move that into your beta naught intercept term. They're not autocorrelated, because if there is an autocorrelation in there, we can have a better model and it'll work, because we can have a little bit of autocorrelation that we can model. There aren't any there the errors are unrelated to the predictor variables. So if your errors are related to the predictor variables, you can play a little more with the predictor variable and get the error down, which is different words for in use like information. Assumptions. Uh, it's kind of nice if our errors are uh, normally distributed, and of course we'd want a mean zero and a constant variance, so we can get better prediction intervals. Sitting around this assumption um, that we make in linear regression is our X predictors are not random variables. Now, if you're working in a lab or a factory and you actually can make settings on a machine that you're fiddling around with, that seems pretty reasonable. However, you've got to sort of uh, uh, hope these formulas work when you throw these numbers in. If you're dealing with business and economic stuff, um, yeah. Uh, so it's not possible to control the value of x. Just observe it. Hence, we just kind of call this an assumption, like, uh, let's see. Now, there's a method called least squares. Um, One way to describe it is, and all kinds of math works out nice for least squares. Um, we look at our model. So this is our air term. We solve it out and we put the y on the other side. We sum them all up, and there is a set of betas which will minimize this. Okay? And of course, you now can think, yeah, I could probably set that up in Excel and minimize it if I had to. And but if it was um, your first thought would be that, but if you were um, wondering if you didn't have a numerical intense system, you might wonder if you could get by with some calculus tricks, and you can. Differentiating and solving it works out pretty nicely, and there are some fairly nice formulas and matrix uh, algebra tricks too, even to get it nicer. So we have our estimated coefficients, and we give them hats. TSLM fits linear regression model to time series data, and it's similar to LM for linear models, but it has some time series facilities in it. So that's nice. Um, um, US consumption expenditure. I looked at this and says, I can't get this in real easily. So um, let's escape this and go to the website and 5.2 and see what I was scared of. I'm scared of making slides. Oh, wow. All right. We had, okay, there's our consumption expenditure. There's our graphic. There's, um, now were we, um, fitted values. Um, yeah, we were just there. Training set, estimated coefficients, and TSL. And here's our data, and I can zoom in, and I can lose this plus. So here's our, we create our our fit with all these terms for the consumption, uh, and then we put that fit result in summary, and we get all kinds of stuff. We get a 5 number, um, yeah, this pointer, that's from, thank you, Google. I have a pointer, and we have a 5 number summary, which is um, of our residuals, which is just kind of helpful. And then we have our coefficients, intercepts, and oh my, things like you might expect uh, for our unemployment. We have negative uh, coefficient. So unemployment goes up, consumption goes down. People with seeing less money try to spend less money. Uh, Not too much about production. Production ends up being a little off schedule. Uh, Income, a big positive effect, and savings, somewhat negative, but relatively inconsequential effect for estimate change. Remember, these are scale to percentage changes too. So these coefficients, sometimes when you put raw data in, the coefficients, the size of the coefficients aren't real um, meaningful because of the scale of the. If you like put somebody's height in inches and their weight in pounds, the coefficients will be different uh, just because of the sizing, and then you'll get a different coefficient adjusted by other numbers, significance codes. Um, we have those like you'd expect in a linear model. Uh, uh, and significance codes. Uh, we have these little dots, and these are quantile codes for p-values. So that's in the report. And residual standard error, we'll talk about that a little later. Multiple R squared, we'll talk about that later. And an adjusted one, and an F statistic um, with a p-value on an F statistic. So this is crazy significant, right? Some very little number that okay. And one instructor says, "How well do you believe that small?" It's like, I mean, uh, do you really have an F distribution model that works that well? No. Well, I mean, I, for checking to see if the forecast is significant, if it actually has some value, which is that overall F statistic would say, you'd say, yeah, there's something there. I mean, it's just, but not p-value. Okay, so for forecasting purposes, the two final columns are of limited interest. The t-value is estimated beta coefficient and its standard error and p-value. Okay, so they're not particularly of interest in there. So back to the PowerPoint. In some ways, this is uh, in some way this is cool. So it is. Yeah, it was better to be able to scroll that table instead of trying to lay it out. So, yeah, wasn't very well contrasting though. Right? Okay, so fitted values. We can run our data and our fitted, and they side by side look pretty close. And I wonder where they came up with those colors. Okay, there are people who do study which colors people should use in their things that you should and shouldn't do. Uh, Sometimes the software people follow the recommendations. I don't know this time if they did. uh, Let's see, percentage change fitted versus actual data. Well, that looks like a pretty good scatter diagram. Well, it was supposed to be. So our fitted data sort of bounces around that. Uh, the straight line pretty well versus, okay, goodness of fit, coefficient of determination. Um, I could almost calculate that graphically. My signature as that little graph, that's how that's done. To make that little cutesy drawing. But the coefficient of determination, um, just go through what these are again. So YT are actual values, Y bar is an average of those. Y hat are the fitted values, and Y bar is an average of those. So this is actually very generic in the sense that anything fitted, anything observed, anything that can be averaged. So you can apply this kind of thing to any kind of um, uh, forecasting kind of rule where you can get those kinds of things done. Um, now, this is one thing. Um, this is then a proportion of variation explained by the regression model. And it's equal to the square of the correlation in simple linear regression. So when we have simple linear regression, it's the same as the square of correlation or correlation coefficient. So you've probably seen this before, and it's bounded between 0 and 1. Now, there's one nasty property with it. R squared can never decrease when adding an extra predictor to the model. So just playing around with that, you may end up putting a lot of predictors in, some that aren't real helpful. When we looked at the plots before, we saw a correlation between variables on that fitted chart. So we have R, and we can calculate R squared. And I think we also saw the R squared, and it explains roughly 75% of the variation in the consumption data. Is that useful? Well, it depends on your application. Note, R squared was 0.6 from the simple regression model with the same data set in section 5.1. So way, way better. So adding the 3 and that A shouldn't be there. Predictors and this T shouldn't be there. Maybe I should get a pen and start marking myself out. 2 mistakes on the page. Save the markings. Have another term, standard error of regression. These are our residuals. We square them and sum them up, and then we divide by t is our number of time periods or total observations. K is the subscript for our max predictor, and -1 is there. So this is kind of like an n-1, but we pull off the K and we have this residual standard error, which gives us another measure of how well our regression fits in the sense of how closely the um, points um, come to the line itself in a plotted value sense. Uh, uh, I was lazy. I didn't want to figure out how to put that hat on in PowerPoint. There may be a way of putting a hat over, but there likely is. But I didn't fight it this afternoon. The differences between the observed um, Y values and the corresponding fitting ones are the training set, errors, or residuals. So these two terms we equate in the book, and they're called residuals, and these aren't epsilons, they're E's, and these now come not from the model, but from these beta hats, these estimates. But they have some kind of fun properties. They uh, they'll sum to 0 if we have these squares, and also when we sum up all the errors times uh, any of the okay, for all k here, any of the uh, predictor variables times the error, it sums to 0 too. This is kind of this leads to a consequence that they're uncorrelated with all of the variables. So yeah, maybe a little marking for my pen for later use. Although I won't likely give this lecture again, maybe I'll use the slides. I'm thinking this 16:9 ratio will stick around a few years. I don't know about O-text though. I only have one book on there. I, uh, another useful test of autocorrelation is residuals. So there's a Brush-Godfrey test, also related to Lagrange multiplier test for serial correlation. I remember working with Lagrange multipliers. I never remember enjoying it. Oh, it's an ugly page full of calculations, right? uh, uh, however, the sometimes people set up tests one way or the other. Um, you either assume that there is autocorrelation or you assume there's not. This one assumes there's not, so when you get a small p-value, it means there's significant autocorrelations. And I didn't look up how to pronounce that today, um, the first word brush, but brioche, So histograms, always a good idea to plot a histogram of the residuals and, well, a rough check of normality. When you get very large amounts of data, your formal normality tests, and there are many. I think I saw one reference that there had been like 50 developed over time. Uh, do you want to look those up? Uh, if you want to check out academic papers, it might be. Uh, but histogram check might be good, or a few other simple plots might be worth looking into. Oh, there's a histogram. Dot plots underneath, a fit line for a normal. Those residuals, normal isn't hard to believe. And, oh, I left something out. I think I'll probably catch that next time I go through. Um, um, so we have the dates. We plot the residuals over time. Look a little flat here. Seem to bounce around a bit too much here. Maybe we don't have, um, well, these were actually times of somewhat great transition economically. I'm 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 just putting these things together time-wise and realizing something like the economic times of uh, around 2006, 2008. You guys don't have a true memory of uh, it's no, because you just didn't have that uh, um, curiosity about news. Generally, so it isn't a worthwhile reference. It is entirely possible to, take a fifth grader and train them into certain things, um, if you have the right circumstances, but it's not worth referencing. And here's our parallelogram autocorrelation function, and wow, right around 7, we have a little bit of autocorrelation in there. Um, so we have one to test back 7. 7 quarterly. That seems a little odd. Um, so and this is just a built-in check residual function. So that's kind of nice. Um, so also the following on with the check residual function, the Bush-Godfrey function. Residuals from the linear regression, the LM test is equal to 15, which doesn't really tell us much. Degrees of freedom, 8, which means it's up to order 8. And then a p-value of 0.06, which tells us a real annoying result. This is what you're supposed to comment a whole lot. The p-value is generally about 0.05. Is what commonly people will use for letting someone publish an academic paper. Significant result. However, 0.06 isn't that much different. And what happens if we just happen to choose our data, sample data a little different? We might kick it on the other side of 0.05. So do you have a problem? Don't you? Like maybe, but not really. So borderline. So residual plots against predictors. So a lot of things we can try. A simple way is to examine scatter plots. So take all of our predictors in the model and see how the residuals work out. If we see some pattern we don't like or something systemic going on, you can see that. Now, you might actually see a pattern in residuals that against predictors that aren't in the model. What does that tell you? They should be there. So you might want to consider adding it. So residual plot. So here's some example residuals. The residuals of our fit versus income, production, savings, and unemployment. And I don't think any of them look too bad. This one, I don't know. Fitted plot of residuals versus the fitted value should show no pattern. If sometimes a pattern is heteroscedasticity, your pattern isn't necessarily in the form of you could draw a line through it, but the bounds would indicate that the variance isn't constant. Okay, so you might need to transform the forecast variable. Ouch, ouch, ouch. Transforming a forecast variable. That, of course, gets a little bit iffy. Your prediction intervals then in your real observable sense get asymmetric, and that isn't always isn't always a clean situation. So here's a little bit of we seem to have a wider variance, around here than we do, let's say, out here for this scatter diagram that I'm trying to think of what this looks like, but I'm looks like some kind of bug or something to me. Okay. Always, uh, the previous software we had for the to allow people to live log in um, put the information in panels on the sides, and then you had uh, center area where your slide showed up. So you never had to worry about anything getting covered over. So my bad habits in producing slides have been not adjusted for this. So outliers and influence variables. Um, this term outlier, it take extreme values compared to the majority of the data, and it's almost generally left commonly ambiguous. Uh, different authors use it a little differently. Just last night in my LLC class, they introduced the term and gave it a specific definition, uh, which is which is okay, but for that particular class. But I had I had to mention that terms differ again. Depends on what night of the week it is. So, observations that have a large influence on the estimated coefficients of a regression model are called influential observations. So usually they're outliers in extreme x direction, and we'll have a drawing like this. So we have this one outlier, but it's right near the center, and it might think of dragging this line down a little bit. However, if we shove it across, it pulls this line way down. Okay. Now you remember these are least squares. So one point that's far away has a great deal of influence. There are other schemes for doing regression, but least squares, outliers, influence variables, they do not do nice things for you. So spurious regression. This always makes kind of a fun question. Give an example of a spurious regression. So you can come up with any strange kind of thing you want. So it just so happens with these trends that air passenger data in Australia appears to look like rice production in Guinea. Oh my gosh. And when we plot the scatter diagram, they look like they follow. So if we're an Australian airline and we want to make more money, we should go get those farmers in Guinea to plant more acres of rice. Is this thing? Uh, well, this just happens to be spurious. Uh, you could just go and maybe look for things that have increasing trends over a time period and match them up. Uh, and uh, that's what these folks did. So the residuals, and wow, it looks like there's a problem here. High autocorrelation on the residuals. Hmm. Uh, Seem to have a pretty good symmetry. But we do see a pattern here in this plot. So um, for those residuals in that fit, uh, they both trend upwards. However, yeah, there's nothing to do with it. Now, the spurious regressions might appear to give reasonable short-term forecasts, but usually off into the future, of course, becomes kind of worthless. Okay. Uh, you know that dry years where you don't get as much rice, it may not affect the air travel too much. uh, I don't. Now, they go through a section here on useful predictors, things that we can throw in and make some adjustments with and put them in our models and how to play with them. Uh, it's common for time series data to be trending. So we may just want to make an X out of our T. Okay. So just a line over time, a trend. Put it in our model. Um, Looks like some guy forgot to finish his slide. uh, they can be specified in the TSLM function. So uh, we do have that, and the book has a little more details in specking it out in um, FPP2. Predictor is a categorical variable taking on only two values, yes or no. And we call those 0, 1s. We give them 0, 1 values, and we call them dummy variables or indicator variables. And they let us put things in categories to describe what's going on. You may want to think of the business on a restaurant. Uh, Nearly every restaurant you think of will have, based on day of the week, different uh, patterns of sales. Some might do that Sunday brunch up real big. Some might do uh, lunchtime for office workers. Some might be the weekend date place. Just um, somebody when we were downtown and I finished my slides early for class, I sometimes walked over to Pita Pit to get something to eat. uh, so and okay. So this is how you do a uh, uh, seasonal dummy variables. Now with dummy variables, there's one thing that is always a little bit odd. You have to throw in a 0, 0, 0 case each time. sort of default. So if it's nothing else, it's Sunday. Okay, and go onward. But this is it. This is the day of the week. Um, and dummy variables 1 through 6. And then Sunday, if none of those click in, it's Sunday. Um, what can we do? If we fit this model here, a quarterly model, which we need 3 dummy variables for, okay, for quarters, and just a trend, we get this fit model to our beer production data that we've seen earlier on, Australian beer production quarterly. And it looks pretty reasonable. Let's see, did we get some other information about it? We can plot actual versus fitted, and they look pretty well correlated, and we tend to actually make the most beer in quarter 4 and the least in quarter 2. But that's how the fitted and actual works. So that's a pretty useful plot. There's also, we can do if strange things happen. Okay. Model, your competitor starts advertising a whole lot, or there's a big industry scandal, so on in the news. It might affect your sales. We might just have a 1 period spike. Okay. And just the one in that period, and we kind of handle it like a dummy variable handling an outlier. So we put that in and let that model out as something essentially taking out that one time spike. That um, um, lost my thought there. So other interventions have a level shift, and did I go to there? Yeah. Other times we have a level shift and we have to make it sort of a step function, and you can also have a step function related to change of slope too. So trading days in a month, so in certain businesses they're just open Monday through Friday and close on the holidays. So you may have a holiday-rich month. Um, and I guess these would vary country to country. Um, in the Philippines in December, it's a little hard to get to the bank because they aren't open that many days. And I remember my son saying, "Oh, I have to go to the bank. It's today." So, otherwise, I can't get there for 5 days. Uh, Distributed lags. So sometimes if we have like an advertising expenditure, a big event, it might carry on, have a lag effect for months. Um, okay, so yeah, I was trying to think of a story to tell, but I done, haven't quite got that together there. Easter. So most holidays are on like the same day each year, or something with a kind of nice formula, like the Monday holidays are the third Monday or the fourth, or and Thanksgiving the fourth Thursday, or whatever it works out to be. Um, However, Easter, you kind of have to code that one up each time, otherwise, or reference some astronomical effect because it has to be. Uh, it's the Sunday after the first full moon of spring. There's a technical way of saying when spring starts, um, and you can include that in the definition, but it's roughly there. Um, uh, it's kind of set that way. So on the days before Easter, you would have a lot of light for walking to evening church services, which there are a number of. So, okay, I, yeah. Um, so, so sometimes it's in March, sometimes it's in April, uh, and uh, sometimes you need a dummy variable. Uh, yeah, so to be very careful with what you do with it. Oh, well, for the electrical engineers in the group, it's something comfortable and familiar, right? Foyer series. Uh, you can actually use those, and there is actually a foyer function term in the um, the package we load for the class. So FPP. Uh, so we can throw those in to handle our seasonals in some sense. Uh, and they say it may work for very long seasonal terms pretty well. Um, for me, that's kind of a distant memory, but it did show up here. Now, sometimes predictors somewhat interact. Um, you don't want to necessarily throw them in one at a time. Um, So, how do we do this is a very, very tough question. I'm thinking I'm finishing early today. It's only got like 670 slides. Well, uh, see, another common approach that's also invalid is to do multiple linear regression on all the predictors and discard those which don't have a high enough p-value. Um, now, the statistical significance doesn't always indicate predictive value. It's not a good strategy because the p-values can be misleading when we have correlated when predictors are correlated. So there are actually 5 measures of predictive accuracy. R squared doesn't allow for degrees of freedom, so adding any variable will increase R squared. And for that reason, maybe we shouldn't use R squared. But there is an adjusted R bar squared. Um, um, and here's an adjustment with N and K, which it is kind of amazing how statisticians see N. We're using T here for that number, our number of observations. So in this chapter, that should be a T, but statisticians tend to think of N as the number of observations so commonly that they didn't correct that in the book. It should be T here for this chapter. So adjusted R squared, a cross-validation, a scheme, and it's actually an older slide. It looked prettier now because they got to stretch it out a bit. Remove observation I from the data set, fit the model using the remaining data, then compute the error for the admitted observation. This is not the same as the residual because the ith observation was removed. And repeat for all n, and then compute the MSE for that. So we have a different mean squared error, and we might call this the cross-validation term, or the CV. I haven't looked up this pronunciation in a while. Akaike has an adjustment on the sum squares error, and they make a note that although this is a common formula, some computer packages have slightly different definitions. So one of those things where 2 different computer packages will give different outputs. One thing that shows up very early on in statistics, when you ask different computer package how to do a histogram, the defaults it'll choose are different from another. And that gets a little unsettling for some students. And the differences between them are actually surprising for people who are even familiar with both the data and the plotting system. So there's another corrected form that works better for small values n, bias correction. And this is one that seems to be preferred by this textbook. There's also Schwartz's Bayesian information criteria, which looks not, oh, who's here? Should we look? Brian Ace. Robert made it today. Looks like you've got a camera on, Robert. Okay. Robert wants his camera off. I'm the guy with the camera on. that's it. Well, to obtain these measures in R, use CVFit. So just straight R would give you that, whatever model we use. So this is actually a first edition slide they use to break green like that, and I just dragged that one over. So this is also a first edition, and this 5.3 probably shouldn't be there because we're in a further section, so I should cross that off. It's tempting to just drag the old slides. It's not wrong. It just leads to mistakes. So there was credit score example then, and what kind of predictors would help us get our credit score up, if we included them or not, and they appears that our best fitting by like the CD criteria is to include all the elements in the model. So, but all of them tend to run pretty close in this. Well, when we leave a few things out like savings, things drop out real seriously. So, now there is something called best subset regression. So all potential regression models can be fitted and the best one selected based on one of the measures discussed here. And these are best subsets or all possible sets regression. And they recommend using cross-validation, a chi-k, or a chi-k corrected. When n is pretty large, they'll all work out to be the same. This is more common in software packages, the Akake index rather than the other, at least in this author's experience. And this book was just, the second edition was actually under development just 2 years ago. 4 years ago, it wasn't there. So So it's a pretty reasonable um, the influence of the authors may go far beyond the price of the book. Uh, okay. Uh, Stepwise regression works quite well, called backwards. Start with the model containing all potential predictors. Try subtracting one at a time. Keep the model if it improves the measure of predictive accuracy. Iterate until no further improvement. Okay, so we can go with a stepwise backwards approach. And there was a slide that showed up here. We saw this. I think the other, much of this, R squared's widely used, selects too many predictors. So we like to stay away from it. These three are pretty good. We've seen this before. If the T is large enough, it'll lead to the same, or maybe it was N. All right. In most of the examples in this book, they use the Akaike corrected for selecting the forecast model. So we'll see more of that. Um, Now, so we looked at the edition 1 example. We can look at edition 2 example. The U.S. consumption with the 4 predictors. So we have 16 possible models. We're all fit, and we have a table there of 0, 0, 1 predictors. And they've been sorted according to the Akaike index. And there we have it. Putting all the predictors in the model, all 4, appears to be the best. We do see somewhat of uh, a big jump here. Uh, when we pull the savings out for the first time, uh, big downward spike. So that's somewhat noteworthy. U.S. consumption, the best model contains all 4. There's a clear separation in the first 4 rows and those below it. This indicates that income and savings are both important variables in production and unemployment. We somewhat saw that in we saw that in the size of um, the size of the beta estimates even. Um, so maybe we could possibly drop production and get similar forecasts. Production and unemployment are highly negatively correlated. So most of the predictive value of production is also contained in unemployment. Uh, looking at the p-value saying this predictor is statistically significant isn't um, always just because it ends up being statistically significant with fairly large uh, t-value, number of observations, we might not actually have it being all that helpful in building the model itself for your forecast. Um, also, the procedures. Okay. Um, now, um, when you have a complex model, any one predictor's influence is not doesn't describe well. It's very hard to say what kind of influence it is because it's in a complex model. And they do, for this discussion, they do note, main author Hinman in computational statistics and data analysis. Um, and he actually links himself, right? Nice of you to put your paper up. Okay, I don't have to buy it then. Okay. However, and there's a book they reference to just for this section. Section 5.6. We can make our predictions using our actual observations with our estimated coefficients. However, we don't really have any statement about the error in the regression equation. We have a couple of terms that get defined here. Ex ante versus ex post forecasts. And it's one of those times when I realize I don't do much and teach this stuff. Ex ante forecasts are those made using only the information available in advance. For example, our ex ante forecast for the percentage change in US consumption quarters following the end of the sample should only use the information up to and including 26 quarter 3. These are genuine forecasts made in advance using whatever information is available at the time. So those are true forecasts. Ex post forecasts are those made up of later information on the predictors. Ex post forecasts of consumption may use actual observations of the predictors. Once they have been observed, these are not genuine forecasts, but used in studying the behavior of forecasting models. So we have this term ex post for letting us be used non-genuine forecasts. Comparative evaluation of ex ante and ex post can help separate sources of forecast uncertainty. This will show whether the forecast errors are risen due to poor forecast of the predictor or the poor forecasting model. And this is as far as I got for this week. And 75 slides got through kind of quickly compared to other weeks. But so we'll pick up this discussion in a couple of weeks and end early this week. And there'll be an exam. Probably should go to the pen. There's a exam next week. And how this will work. If you're a distance student, you make arrangement to get the exam from generally a true distance student from Crystal, and we send it to a proctor, which you had approved. And I've had a few people have those proctors approved, and then you take it and then you send it back, and I grade it. We will have an exam in the classroom, and anyone taking the course in any situation can come and take it. Although we only have 2 people registered on site, and we are often seeing just one, I think maybe some of you, as a convenience, may come in and take the exam on next next Tuesday night. That, however, usually what I try to do, I try to get in the room about 5 in case somebody wants to start early. This exam, time-wise, is a little shorter than most. There are generally like short answer, fill in the blank kinds of things, not nasty calculation kinds of things like um, first exam last fall. So we'll um, uh, so I'm guessing that although you might want to have a question or two you might want to ponder looking up to fight it. It will probably run shorter than most of the exams had in other classes. So and yeah, I don't know how many people will show up for sure. I guess I could guess a little. They do give us some information about our students. They they might be on site or not. We'll see. So exam next week and done for the week. Okay. So what will we do? Stop recording.